on this little thing Q. Now, rank the magnitude of the electric potential at points A, B, and C from greatest to least, with number 1 being greatest. So, what is the equation, the general equation for electric potential? Yeah, KQ over R. So, if this is the same Q, that means that should be the same for all three, so then it's a function of R. Therefore, B should be greatest, and then A and C should be second. And they should be equal because they're both the same average distance. All right, cool. Yeah.
I'm so like,
Good. You should be pleased. That's good. Okay, does that make sense to everyone? All right, very good. Then point P at the origin is shown below, and is the center of curvature for the charge. Okay, that's for the charge distribution. Determine expression for the electric potential at point P due to the charge Q. Well, I immediately begin to think, okay, we have to integrate something and create some expression, right? But when you look at it, the radius is the same from everything. So then I can sort of say, well, it's just like adding up all of this Q for this R. So I would think that we can just say it's KQ over R. But
I'm so smart for playing something so simple. To do this to us. This is so hard.
Is this it? So let me see, everyone.
Yes.
Was I right about this? Yes.
Yeah.
B is 1, A, and C. Then for part 2, I want to show
Part 1 and 2 both right. Oh my god.
Okay, so for part 2, yeah, we just use KQ over R.
So smart.
And then this is the crazy calculus way if you want to do that. So basically, and we've done this before, right? We did it with moment of inertia. We also did it with the electric field from a certain charge. And it's just you take the function and then you integrate that function, right? Especially since it's a sum function, like you're adding up all the charges. So they're just taking the equation, which is K over R, KQ over R. But all of the Q, we're not interested in the whole thing at once. We're interested at some differential unit of Q. Does that make sense? You must be hanging around Jack. Why am I saying that? Because he always says that. What's that?
But you don't do the hand popping thing.
Yeah.
What's that?
He, like, they'll talk and he'll put it in, and he'll talk and
Oh, really? Oh, he goes like this?
Yeah.
That's because I don't wear cargo shorts with big pockets. It's kind of too much of a pain. I don't know. Okay, maybe smart people have to hide their hands in their pockets. He actually has like a system in his pockets, like that has like the next question. Okay.
So is lambda just
Oh yeah, so I'm getting there. All right, so we have KQ over R, but then because we're going to integrate, right? We don't just want to guess that it's Q. We want to actually take the effect, the electric potential caused by an infinitely small amount of charge along that curve. So we say, all right, well, what is dq? How do I come up with that? Well, does it make sense that we can use, do you remember when we did this for moments of inertia? We used the density. Remember that? So once again, we're going to use the density, which is lambda. Lambda is the amount of charge per length. And then they do this little slip thing right here. What is r d theta? What is r theta? What does that give you for a circle? Yeah, it gives you the arc length, right? So what we're doing is we're saying a little tiny piece of the arc length. So then we're using the density, which connects that to the little tiny piece of the arc length. And then that gives us this 2q over pi d theta. So you integrate that and you get the same answer.
Mr. McClure,
Yeah.
would it be instead of if we said instead of K, we use like 1 over 4
Okay, questions? To be honest, I did not think this way. I just thought that way. But that might be because I've been teaching B for 15 years. Okay. Now, a positive point charge Q with mass M is placed at point P and released from rest. Derive an expression for the speed of point charge when it's very far from the origin. do you see what we're going to do here? This is just, well, okay, think of what you just said. I appreciate your answer, first of all. Thank you for that. KQ over R gives you what? What does KQ over R give you? Electric potential, or V, right? Voltage. And you just said that equals what? What does that give you? Kinetic energy, right? So do you see the problem? See, KQ over R, if you set this equal to 1/2 mv squared, the problem is you've got volts equal to joules. Now, don't lose hope yet, right? Because if this is the first thing that popped in your head, it's actually a pretty good thing. What do I need to get volts to work? See, what gives volts, what turns volts into joules? Right? No, not Q. Yeah, it's coulombs. Right? So if I can get coulombs times volts, I'm good. Now, do I know the volts at point P? We already determined it, right? Remember in part B? Drive an expression? No, that's not it. Part B. Yeah, determine an expression for the electric potential. We already came up with V. So, you told me, thanks to your logic, that if I could do coulombs times volts, I'm going to have joules, right? So since I already know this is V, all I need to do is say V times Q is going to equal 1/2 mv squared. Does that make sense? Yeah, see, so you were 2/3 of the way there. Just check your units and they're good. What's that? No, this is the energy.
Oh, that's potential energy.
Yeah, because remember, like, how else could I, like let's say I take a neutral particle, I crack it into plus and minus, right? How, and then let's say, I don't know, like I take away this, so I just have this plus. What is around this plus?
Electric field.
There's an electric field. So does it make sense that I can calculate the potential energy between, if I bring the minus back, between these two things? Okay, well anyways, yeah, oh actually we kind of did it, all right? Because we did our expression, all it is set the velocity, the kinetic energy equal to the voltage times the charge, and then for part D, indicate the direction of the electric field at point P. It must be like this, right? Because the charge is positive on Q. And derive an expression for the back. Crap, I can't do that. All right, see you tomorrow. Bye.